What's up? What's up? It is note-taking time. I am running short on time, so I have a video that has almost everything that we did today, so I'm gonna cut it right in after this. But first, make sure you take that for the agenda, and then also just know that I am going to put this journal check into the I'm gonna put it into the modules for tomorrow because I have we're gonna be doing the lab tomorrow. So since we're gonna be doing the lab tomorrow, they don't have time to actually check your journals while you guys are completing the lab for tomorrow. So yeah. So what's the last thing? Oh, hold on, pause. Let me remember. Oh, the last thing is I was able to get a lab for this on its own whole separate video. So that is already posted up under Tuesday. So under yesterday. And then I'm going to cut right here and I'm going to splice right into the other Mr. Farr teaching this whole lesson for you guys. Peace. Wait, get to the next one. Hey, what are you doing? You're supposed to be in the next video. This Explorer will be posted in its own whole video, so I'm not going to take any more time to talk about this one. But again, page 83 and 84, mass and gravitational force. We will finish recording this today, and then I will see if I can get it edited, and I'll for sure get it up tomorrow, maybe today. So we'll see. So anyway, but this is, this is what we're going to complete today in class. Then we're going to move on to this next part. Okay, so let's just talk about this. These are notes that you should already have inside your journal. So flip to your journal. We're gonna have notebook, journal, notebook, journal. So anyway, flip to your journal. These are notes you should already have inside of your journal. So this thing about force is a push or a pull that can change the motion of an object. Remember, weight is the heaviness of an object, and that is the force of gravity on the mass, right? So the force of gravity pulling down on an object, that's what the weight is. Interacting objects, let me see if I can, boop, boop. All right, so objects that affect one another, and then mass right here is the measure of how much matter is present in a substance. So any kind of liquid or gas or solid, like how much mass, how many molecules, how many atoms are in there. So these are all things that we already know. Let's move on to some new things. All right, now this is where you actually got to start writing your journal. So I'm going to talk about the slide and I'm going to move on. You pause it as you need to, okay? So gravity, this is something that we have been talking about, and now we're just going to actually put an actual definition to it. So gravity is the force that causes objects with mass. So if an object has mass, to attract to one another. So gravity is an attractive force. Like magnetism, like a magnetic force, gravitational force is also very the same way. And remember, it's a force that's at a distance, right? So the objects actually don't have to be touching in order for the gravitational force to be pulling something in. So the force that causes objects with mass to attract to one another, okay? So that means that if the object has mass, then it has gravity. I know this is a mind-blowing thing. We'll talk about it a little bit more. But obviously, the more mass you have, then guess what you think about its gravity. All right, so that's what we're going to talk about in the next lab, right? So again, gravity is the force that causes objects with mass to attract to one another. All right, cool. Attractive, so we just talked about that, attractive. So having the tendency to pull other objects toward itself. So the more attractive a magnet is, then the more objects it will pull towards itself, or the larger the object it will pull towards itself. So depending on how big its attractive force, so that could be magnetic or gravitational, then the larger and the closer other objects it will be able to pull towards itself. And again, pause the screen if you need this. I'm gonna move forward. Okay, cool. Let's go here. So let's talk about this for a second. Scientific notation. I'm going to try and move myself up out the way, and let's go ahead and watch this video, yo.
Welcome to Moo Math and Science. In this video, I'd like to talk about scientific notation, an easy way to write big numbers. Bill Gates has a net worth of $93 billion.
Woo, that's a lot.
This is a large number to write. A nanometer is 1/billionth of a meter, and it is written like this. Both of these numbers can be rewritten using scientific notation. Bill Gates' net worth can be rewritten as 9.3 times 10 to the 10th. A nanometer can be written as 1.0 times 10 to the negative 9.
Now, part of the reason why we use scientific notation, if you look over there, it makes the writing more condensed. As opposed to writing out this long old number, now we can put it in scientific notation. Now pay attention to the way that it's explained, why this exponent over here is positive and why this exponent over here is negative. Pay close attention to that part.
9. Let's go over some of the basics of scientific notations. Up first, the coefficient must be between 1 and 10. The exponent can be positive or negative, but it must be an integer.
Okay, so just so you guys know, the coefficient is this number that's out here out front. So you got the 9.3 times 10. So the rule is for scientific notation, it needs to be between 1 and 10. So it can't be 10. It's got to be less. So you would move it all the way. So like you can't be 93. You have to move it all the way to the 9. So 9.3 times 10. And then when they talk about the exponent, right here, this part right here has to be an integer or it has to be a whole number. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, on and on and on. No decimals. Has to be a whole number.
If you have to move the decimal to the left, the exponent will be positive. If you move the decimal to the right, the exponent will be negative. So let's look at 530,000. In this example, we do not have a decimal, so we can assume it's after the last zero. The coefficient must be between 1 and 10. So we need to move the decimal 5 places to the left, because 5.3 is between 1 and 10. The exponent will be positive, because we moved the decimal to the left, and it can be rewritten as 5.3 times 10 to the fifth. In this next example, in order for the coefficient to be between 1 and 10, we need to move the decimal 4 places to the right.
Yep, to the right.
7.8 is between 1 and 10. We need to move the decimal to the right, so the exponent will be negative. So the scientific notation will equal 7.8 times 10 to the negative 4. So there we go, some basics of scientific notation. Thanks for watching.
No problem, sir. No, thank you for your explanations. Okay, cool. So we're just going to move it along. So take this as a note right here. And again, I'll just walk through this again. Is this idea that that the coefficient, whatever's out in front when we do the scientific notation, is that must be between 1 and 10. So if you look right here, this is between 1 and 10. So 9.3 times, again, 10 to the an integer. So and we'll talk about that on the next slide about the positive and negatives and when you know to put that, right? But if it is positive, then you're going to move the decimal place to the right. So you're going to be like this. So you would be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And if it's negative, then it would move to the left. So make sure to get this note in there, and that note goes with this next note. So peep this. So, and this is exactly spelling this thing out. So, if it is, right, again, if it is negative, then that means we had moved this decimal place, boom, 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 to the right, like from this original number. So if you look, it says -5, so that means we went 1, 2, 3, 4, 5, so that's 6.0, and that's what you see right here, times 10 to the -5. And again, in order to get it back to the original number, you would have to go -5 back the other way. So 1, 2, 3, 4, 5. That's the logic in it, okay? So again, you have this number right here, and you're gonna go, this is 5, so it's going 1, 2, 3, 4, 5, and that would be to the left. That would make the number positive. So again, if you move the decimal in the original number to the left, then that's going to be positive. And if you move it to the right, then it is going to be negative, okay, when you're putting your exponent in. And if you look at both of these numbers are between 1 and 10, right? And then also this is a whole number or an integer, right? So again, it can't have any decimals, but it needs to just be a whole number. All right, cool. So we are going to take a little practice, flat out. So give yourselves a couple of minutes, pause the screen, get these rewritten in scientific notation. Remember the rules we just went over. Get these rewritten in scientific notation, okay? All right, let's talk about this for a second. So for this first one, to get it to scientific notation, we need to get it to be between 1 and 10. So that needs to be like 1.23. That's what we need to do. So we got to move the decimal. Hold on. We got to move the decimal. 1, 2, 3, 4, 5, 6, 7, 8 places, right? So it'd be 1.23 times 10, and since we had to move it to the right that way, right, since we had to move it this way, then that's going to be negative, right? So 1.23 times 10 to the negative 8. There we go. Okay, now over here, are we moving this to the right or to the left? That's the first thing. We got to, in order to get this to be between 1 and 10, we've got to move this to the left, right? So let's just count how many places we're going to move. So 1, 2, 3, 4, 5, 6, 7, right? So that'd be 4.56 times 10 to the what? Hopefully you got to the 7, and that would be correct, all right? So cool. So we will practice with that a little bit. I just wanted you to understand, because you need this for the next lab. You will, thankfully in the next lab, you don't actually have to do that, but you'll need that for the next lab. Okay. So we're going to go over this word. I'm assuming you've had it before, so go ahead and write it down. But again, a hypothesis is an unproven theory, a statement, or a prediction, okay? Again, it's an unproven theory, statement, or prediction, or what we might call it an unproven claim, right? So again, it's something that has not been proven yet. All right, it's just a hypothesis, right? And then what you would do with your hypothesis is you would go and you would try and actually devise an experiment to try and prove your hypothesis or your claim, right? The same kind of thing to be true. So pause the screen if you still need this. All right, we're gonna move right here. So here's the question for y'all. What will happen if 7th and 8th graders take the same 8th grade math test? What do you guys think? What do you guys think is going to happen? So most people are going to say that they think prediction, right, is that the 8th graders will get higher scores. That would be our dependent variable. And you're like, well, what do you mean? Well, what we're going to measure, again, is the scores, right? So we're going to measure the scores. That's what we're going to find out, like, what's going to happen. The hypothesis, if 7th and 8th graders take the same math test, that's our independent variable, then the 8th graders will get higher scores on average. That's what our claim, that's the claim part of it, right? So your hypothesis is putting the whole thing together. If 7th and 8th graders take the same math test, independent variable, again, the thing that we can change, which is the 7th and 8th graders, right? We're selecting who's going to take the test, right? And then the 8th graders, saying that they'll get a higher grade. So the math scores, that's what we're going to measure. And then our control variables, which we did not put that on here, but our control variables would be the test, right? Because that's the thing that we can keep the same. All right, let's move on to the next one. This one I actually want you guys to try and do. Will the number of tardies change if teachers are standing at their doors greeting students? What would you guys say, right? Like, what is the dependent variable in this case? What is the independent variable? What is that in this case? What is that? The independent variable. Go with this. What is your claim? What is the dependent variable? What is the thing we're going to measure here? We're going to measure if the students, right, the number of tardies will decrease. So we think, that's our prediction, that's our claim, we think the number of tardies will decrease if more teachers are standing in their doorway, right? So and we just phrase it up like that. The thing we can control, which is the independent variable, if more teachers stand in their doorway, then the number of tardies will decrease. Does that make sense? Hopefully that makes sense for y'all. The next thing we're going to do, which we're not going to go too much further in this video because it's already getting like long, is this right here. So what I want you to do is just read the directions. Read the directions, and then you can get started on this if you're ready to get started. In class, I'm not sure if we're going to be able to get started or not. I think this is exactly where we'll end. It's probably right here reading the instructions. All right, y'all. Have a nice day. Peace.